Hi, my name is Ming Yao, and this is part 2 of my simulation in ANSYS Workbench. We're looking at a resonator here, and in this video we'll look at how to parameterize the simulation.
So in my Siemens NX, I've parameterized the width and the radius of my springs. So the radius here is 0.2 millimeters and width is half width, I think it's 4. So we can enable these as design parameters. The other spring is a copy of the initial spring, and I didn't specify any properties here for the oscillator. So I want to adjust the spring. In addition, I want to parameterize the thickness of the spring, because that's certainly going to have an effect on the amount of deformation and modes, depending on how thick I make these springs. So once we have input parameters, if I go back to my Workbench project page, it shows I have a parameter set of input parameters feeding into the system. I can also specify my material properties as parameters and any type of loads or supports. I'm going to leave the compression displacement constant for now at 1 millimeter, and I want to take a look at maybe the pre-stress stress, maximum equivalent stress due to that loading. Interesting set of units here. So let's switch to, say, megapascals. So we have 1,000 megapascals as our pre-stress, maximum pre-stress here. For our vibration analysis, we want to know what the first resonant frequency is, but we also want to know we want to have some way of separating out the modes. We want to know whether the first resonant frequency is an X translational mode or a Y-axis translational mode or a Z-axis translational mode for that matter. So we'll switch this to an X-axis translational mode, and we'll flag the minimum and maximum displacement. Do this for the first 3 modes. So flag min and max. And we also turn this into my X-axis translational mode, flag min and max. Okay. Evaluate the results here, and it shows me this is my maximum displacement, and this is the min-max displacement for my third translational mode, my third mode. And for the harmonic analysis, it tells us what the maximum displacement, amplitude, as well as the maximum frequency. We certainly want that. We also want to look at the equivalent stress due to vibration on the 2 springs. So let's get those as well. So I'm only selecting the 2 springs to plot the equivalent stress on. And this right now is shown at a particular frequency. I can say maximum over frequencies. This will tell us the absolute maximum stress across all of the resonant frequencies. And the largest stress should be the one corresponding to the largest displacement. So if we get our resonant frequency correctly with the largest displacement, this stress value should correspond to that. So now we have a number of input parameters as well as output parameters. On the input side, we have the width of the spring, the radius of the spring, as well as a leaf spring thickness. We want this to be symmetrical, so I'm going to change P4 to be equal to P3. This forces the leaf spring to be the same at all times. We have harmonic response analysis, where we're reporting the maximum amplitude, the frequency of response, as well as the maximum equivalent stress. So this will act as a way, a check for our results. We want to, in order to separate out the frequencies and understand which of the first 3 modes is moving in the x-axis, I'm going to add up the directional displacements. So we're going to create a new parameter. This will be P7 plus P8. And I'll call this my mode 1. Create a new one here for adding P10 and P11. This will be my mode 2 participation factor. And then I also want to add up my P13 plus P14. So this mode 3. Okay, so from this data you can see clearly that the most dominant mode in the x-axis, the displacement is the second mode participation factor. Ideally we want the first mode to be the x-directional displacement, and we want this to be high in order to allow the structure to resonate with minimal input. So now we have 4 input parameters and a lot of output parameters. From there on we can do a design of experiment and look at the data that it generates. So we have a few different designs of experiment or design exploration options here. I'm going to go for a response surface optimization because this allows me to automatically create a design of experiment, refine the data from the design of experiment to create an accurate response surface. Then it has a set of post-processing tools for me that allows me to dig in and improve the design. So let's get started with a basic design of experiment study. A design of experiment allows us to specify a lower and upper bound. So I'm going to go from 2 to 5 millimeters here. The starting point is 4, so maybe let's go to 2 to 6 millimeters. We can adjust the radius of curvature. So I'm going to go from 0.1 to 0.5 millimeters, and the spring thickness. So let's go from 0.1 to 0.75 millimeters. Maybe I'll make this a bit thicker too. We have a number of different design of experiment options available. I'm going to start with a very basic central composite approach, which ANSYS will generate a DOE matrix for me. So we're going to do 15 simulations. Each of this, ANSYS will modify the CAD geometry at each time, run a simulation, and it has a number of, it'll fill out this parameter table. So let's go ahead and update this. Okay, so the simulations are done. We have a full set of 15 analysis with a static structural pre-stress followed by modal analysis, data on the first 3 resonant frequencies, as well as the participation factor, and a harmonic response simulation to look at stress and deformation. So from there we can carry on with our design exploration. So the next thing we looked at is we will look at is a response surface. In a response surface, ANSYS will try to create a response surface, which are equations that interpolates between all of the input and output parameters. ANSYS uses a genetic aggregation technique, which combines various response surface features into a single response surface using genetic algorithm, and in order to try to achieve the best fitting. This also makes it easy for users so that you don't have to try and pick different response surfaces and evaluate how well each particular response surface fits with the data. However, a data set here is fairly limited right now, in that it's only based on 15 analysis across 3 parameters. So one of the key aspects of ANSYS response surface generation is that we're able to create verification points. So we can seed additional points into the simulation automatically, into the response surface automatically, to compare the predicted value to the verified value and see how good our response surface is. So here we can plot some 2D or 3D response surfaces for given equivalent stress, or say the first resonant frequency, or the second resonant frequency, or the third one, and how each of them change with respect to the radius as well as the width. As I mentioned earlier, we want to go back and do some more simulations. So I'm going to add another, say, 16 simulations to verify our analysis. So now ANSYS will create, based on the response surface earlier, it'll create an additional 16 verification points. This is the goodness of fit curve. If everything is as predicted, all the data would lie right on this curve. Here we're going to do an additional 16 simulations, and so it'll show a distribution of how good the fitting is. And if it's not good, we can take that data, turn them into refinement points to improve our response surface. Okay, so the verification points have been completed, and we can see that there are certain verification points that lies far away from our estimates. That's okay, because we can select these verification points and convert them into refinement points, which will then, the data will then be used to refine our response surface to come up with an even better estimate. So here we're copying it over, and we'll do an update. Okay, as you can see from the new fit, we no longer have such wide disparities between our predicted values and the actual calculated values. So we can repeat this process by adding additional verification points to the simulation and repeating this process. You can look at the response surface calculated. For the purpose of this demonstration, I'm going to assume that the response surface is correct. Let's take a look at, for example, equivalent stress, or some additional bumps and notches. We look at design points for the response surfaces. So once we have the response surfaces, we're able to now get more meaning from the simulation. So under Optimization tab, we can just define various objectives. Here I will select to maximize the first mode participation factor. This allows us to confirm find designs where the first mode is moving in the x direction, an x-axis translational mode. Then we want to minimize the first mode frequency, resonant frequency. And finally, we also want to minimize the stress involved in order to make sure we have a long life in our design. In a response surface driven optimization study, we have the option of performing a screening analysis where we assume the response surfaces are correct and randomly pull thousands of designs from the response surface. Here I'm going to pull 3,000 designs, and then performing an optimization analysis based on this data. The other option is a multi-objective genetic algorithm, which will require repeated solves of the simulation. It's certainly more accurate, but it will be very time consuming compared to my screening method. So with this decided, we can go ahead and hit the update button. So ANSYS is now performing a screening analysis and try to find the optimal designs for me. In addition to finding optimal designs, it will also provide a number of other post-processing techniques, such as trade-off plots, sample, or candidate points. So let's take a look at the first option here. First set of results shows me the candidate points. It picks 3 candidates for me, and it shows me the amount of displacement, the stress, total deformation frequency, as well as participation factor and equivalent stress values. So one challenge with dealing with large number of parameters is that you end up with a lot of data, so it's difficult to make sense of it. And that's what these post-processing options are for. So for example, in the trade-off study, I can plot a trade-off between participation factor, as well as the first resonant frequency. So this is my participation factor, and this is the first mode resonant frequency. If I want a low value with a high participation factor, then I'm looking at this particular set of lines. But you can see there's a wide spread. This trade-off study also shows me that anything within this block, this area, surrounded by my trade-off plot is possible. So I can find any given frequency, for example, 1 kilohertz. There are a series of designs that represents at around 1 kilohertz, and click on any of these and get the design that would lead to that particular resonant frequency as well as participation factor. I can look at a sensitivity plot which shows me for each parameter, each output parameter, what are the most important input parameters. For example, the first few output parameters, 4 through 6, are, well, let's look at 5 is the equivalent stress value, 6 is the total resonant frequency. The last few parameters here are my participation factors. So the first mode is primarily driven by parameter number 1, which is the size of my spring, and to a lesser extent, the thickness of the leaf spring. The second resonant frequency, the factors are inverse, while the third frequency is primarily dominated by my leaf spring thickness. So a sensitivity study gives you an idea of how different parameters will respond to different inputs. Finally, my sample results here has many columns. Each column represents one set of parameters, so you can see we have P1 through P20 here. What you can do here is filter out designs that you're not interested in. For example, one of the key things we want in our particular design is to ensure that we have the first resonant frequency in the x-axis. So let's go ahead and filter out any design where the resonant frequency, where the participation factor is low. So we have a minimum and a maximum value here, and I'm filtering out designs where I want a significant gap between the first resonant frequency participation factor and that of the second. From there, we can look at the resonant, picking the proper resonant frequency. That'll be P6 here, my first resonant frequency, my first mode resonant frequency. So here I can pick any of these modes here. Let's say we have a range here. We also want to ensure that we have good durability, which means we want to minimize the equivalent stress, which is P17 here. You can see that we already have a fairly low set of stresses. I can select one of these designs. And if I right click on it, I can insert this as a design point. By inserting this as a design point, ANSYS can perform a new simulation based on this and confirm our estimates. So I want to ensure that we retain the data here, and we can now run a simulation on this design point. So here ANSYS will update the geometry in Siemens NX. It will set up the static structural, followed by a modal and a harmonic analysis, and report back on all the results that is calculated. Once the simulation has been completed, we have a full set of data here, including the input parameters as well as all of the output parameters. You can see going to the back here that our first mode participation factor is indeed fairly high. Right click on this, setting this to current allows us to see the resulting simulation. So this is the new design. You can see that it's slightly thinner and we have a larger radius, and the spring is slightly thinner as well, the wall thickness for the springs. Deformation looks very much like what we had before. We have a modal analysis where this is the first resonant frequency is now 855 Hertz. Second resonant frequency is at 873 Hertz. And then the third one here is a rotational mode around the z-axis. Finally, we can take a look at a harmonic response. It shows a resonant frequency here again at 850 hertz around, and the stress is fairly low at 129 megapascals. So it is as we expected. We have achieved the proper sizing for the system and the desired resonant frequencies.